Hello and welcome back after the break. So second speaker of today is Suraj Krishna from Technion, and he'll be talking about relatively hyperbolic groups, in particular the mapping tori of torsion-free hyperbolic groups. So the floor is yours, Suraj.
Thanks, Mikhail, and thank you for inviting me to give this talk. It's unfortunate that it's only virtual, but okay. So yeah, I'll talk about mapping tori of hyperbolic groups and say that they will be relatively hyperbolic. Everything I talk about today is joint work with François Dahmani. So let me go to the two statements that I want to talk about today. Okay, so throughout this talk, unless mentioned otherwise, G will be a torsion-free hyperbolic group. And alpha is an automorphism of G. Okay, the first statement is, given this setup, there exists a collection of subgroups, which will be maximal. It will be a maximal collection of maximal polynomially growing subgroups. And this will be a malnormal collection. So I will explain what I mean by all these terms. And this will be a quasi-convex collection. So this is malnormal as a collection. So maybe I should say that. Okay, so and the second statement is that the mapping torus is hyperbolic relative to the mapping tori of the above polynomially growing subgroup collection. So okay, so what does this mean? So first, if I take any G in G, and I take this collection, so I take iterates of G under the map alpha, and I take its conjugacy length. So what is this? This is the infimum of the distance between one and conjugates of this guy. So I'm not looking at just the word length, but I'm taking all conjugates of this element and looking at its length. So this is the conjugacy length, and G has polynomial growth under alpha if this collection has the growth of this is bounded by a polynomial in M. And the subgroup is polynomially growing if every element here is polynomially growing. And what this statement says is any polynomially growing element will be in a conjugate of one of these guys from this collection. So this is a maximal collection, and this is a malnormal collection. What does this mean? If I take any G and look at this intersection, if this is not 1, this implies G is in HI and I equals J. given any automorphism of a torsion-free hyperbolic group, we have a collection of subgroups up to conjugacy. Any polynomially growing element is contained in this collection. And this is a malnormal collection and it is quasi-convex. And the second statement is about mapping tori. So what is a mapping torus? So this group, it's an HNN extension. It has this presentation. So take the presentation of G, introduce a new stable letter T, and with the relation that for every G, the T conjugate of G is equal to the image of G under the automorphism alpha. The way I think about this is I have a nice space X such that the pi1 of X is G, and then I have a homeomorphism or a homotopy equivalence of X such that at the level of pi1 it gives me alpha, and I take a cylinder and then I glue the ends of the cylinder by the map F, which is the homotopy equivalence, which is at the level of pi1 equal to alpha. So the mapping torus here as a space is this guy quotiented by so x comma 1 is glued to f of x comma 0, and this group gamma. So the pi1 of mf will be gamma. So the mapping torus as a group is an HNN extension, and thinking about it as a topological space, it's the pi1 of this mapping torus. And so this mapping torus is a relatively hyperbolic group, and it is with the parabolic connection coming from the mapping tori of these polynomially growing subgroups. Okay, so some very quick and brief history. So if G is the fundamental group of a closed surface of genus G, at least 2, then it's a celebrated theorem of Thurston. That the mapping torus is hyperbolic if and only if the map alpha is coming from a pseudo-Anosov map. So in this language, if it is atoroidal. What does atoroidal mean? So for every G in G, no conjugacy class. So atoroidal means no conjugacy class is preserved by any power of alpha. So for every n, alpha to the n of the conjugacy class of G is not equal to G. So if alpha takes the conjugacy class of G to itself, then in the mapping torus, we can see a torus. And this is an obstruction to hyperbolicity. So if G is a free group of finite rank, then Brinkman extended Thurston's result. and the statement is the same. So it's hyperbolic if and only if the map is A toroidal. Okay, this is about hyperbolicity. So it's a strong condition on the map, and we have many maps which are not atoroidal. And for the case of surfaces, in fact, Thurston gave a complete classification of all automorphisms. So given a surface, if the map is not atoroidal, that is, it's not coming from a pseudo-Nassau map, then Thurston's result says, okay, you can break this guy into subsurfaces such that the map preserves the isotopy classes of these subsurfaces, and on each piece, the surface, the automorphism either behaves like an atoroidal map or it has finite order up to conjugacy. So using a combination theorem that I will state later, one can easily see that the mapping torus of a surface subgroup of a surface group is always relatively hyperbolic. For free groups, so this is a theorem independently by Ghosh and also Dahmani and Lee. So if G is a free group, then the mapping torus is hyperbolic relative to mapping tori of polynomially growing subgroups. Okay, so for surface groups and free groups, this result is already done. Okay, let me now explain I'll sketch the ideas of the two statements. So the proof proceeds by induction on a rank of, so it's called Kurosh rank. I will define that later. But let me explain the two theorems in the one-ended case. So a torsion-free hyperbolic group is one-ended if and only if it admits no free splitting. This is a result by Thurston, and we will use that here. And the one-ended case was treated by Gotero and Lustig. But I will explain the proof using this combination theorem that I will state later. Okay, so if G is one-ended, so this is a theorem due to Sela and also Bowditch and others. There exists a JSJ decomposition for G over cyclic groups. Further, this is a canonical decomposition. So there is there is only one JSG tree up to equivariant isometry. So I will just say for the let me just say it's canonical. Okay, what is this JSJ decomposition? So, so this is a graph of groups decomposition. For G with some properties. So first, every edge group is cyclic. Second, the underlying graph is bipartite. Third, so black vertex groups. These are maximal cyclic subgroups of G. White vertex groups. They can be of two types. Either they're like hanging surface. So I will say what it means. I will maybe draw a picture. Hanging surface groups, or they're rigid. And given, so if G splits over a cyclic subgroup, implies every edge group of the JSJ is elliptic here. So these are, so the JSJ decomposition is a graph of groups decomposition with these properties. So maybe a picture. Now I have to be careful to see that it's bipartite. 1, 2, 3, 4, 5, 6. Okay, so maybe some are black. Now I can have more edges between black and white. Okay, so the black vertex groups are cyclic subgroups. Some are, say, this is hanging surface. And some are rigid. Okay, what is a rigid vertex group? So it is a vertex group such that it does not admit a further cyclic splitting over the entire group. So that is why the JSJ is like a maximal cyclic splitting. Any cyclic splitting can be seen from this. And okay, I still have to say what a hanging surface group is. So a hanging surface group is a pi1 of a surface group with boundary. Say something like this. Such that the boundary cycles correspond exactly to the incident edge groups here. So here there were three edges, so three boundary components, and each of them is attached to the cyclic subgroup coming from the edge as an isomorphism. So this is the main JSJ decomposition. And why do we need it here? Well, because the decomposition is canonical. So if I take an automorphism of the group, then it will send a JSJ decomposition to a JSJ decomposition. So black vertex groups are sent to black vertex groups, hanging surface groups to hanging surface groups, and rigid groups to rigid groups. And after taking a power, it sends a black vertex group to a conjugate of itself, and any other vertex group to a conjugate of itself up to taking a power. And once we have that, what can we say? So, oops, I did something wrong. Yeah. Okay. So we want to see where growth is happening. So it sends a black, so alpha restricted to a black guy. There is no growth because this is just a cyclic subgroup, so no growth here. Alpha restricted to a rigid group. Okay, but this is up to conjugacy. So the property of a rigid group, this is due to many people. So Bestrina, Paula, Rips, and Sela. So a rigid group has finite outer automorphism group. So it does not admit more automorphisms. So after taking a power, alpha acts on a rigid group as an inner automorphism. So here it will be an inner automorphism. So again, this means there is no growth happening here. So now we are left with a hanging surface group. And here, the result of Thurston says, well, this piece here, it can be broken into some subsurfaces. Such that on some pieces, say, okay, let me say here it acts as a pseudo-Nosov map, so toroidal map, and here it has finite order. So I will just say identity up to taking power and conjugating. So what I have is so I think I didn't copy that. Okay, and I'll write it again. Black. So this was the hanging surface group. So I can blow up that vertex. So just the hanging surface group is getting blown up into three pieces according to the three pieces here. And the rest remains the same. Now, Okay, now it's not a bipartite graph anymore, but what I do have is that here it acts as an atoroidal map, a pseudo-Anosov map. And everywhere else on each other vertex group, it has less than exponential growth. And now I can collapse the non exponential growth vertices. So I will be left with this graph. So this is the PA vertex, and this is a non-PA vertex. So here, so I'm getting back a bipartite graph where a vertex is either PA or it is not, and PA is always adjacent to a non-PA vertex and conversely. And so what is the point of doing all this? Well, here, every element in this vertex group, it has exponential growth. Every element here, it has utmost polynomial growth. So this gives me my collection of polynomially growing subgroups. Each vertex group of a non-PA vertex corresponds to a group of utmost polynomial growth. Well, in fact, it'll either be bounded or have linear growth, but okay. And a PA vertex, an element of a PA vertex gives me exponential growth, and an element which is passing through two or more vertices will also give me exponential growth. So this gives me my collection of polynomially growing subgroups that I wanted for theorem 1, and for theorem 2. So this guy will be hyperbolic relative to the mapping tori of all the polynomially growing subgroups. And for this, I'm using, okay, let me go to a new page. So this is due to a combination theorem by Dahmani. Okay, there are, I think, 4 cases. I will probably use 3. So let me say, so let G1 with this collection P1 be a relatively hyperbolic group, and G2. So if any of the terms I use like are not clear, please stop me. So suppose these are 2 relatively hyperbolic groups, and I take an amalgam. Where H is a relatively quasi-convex group and it is full, then this new group G is hyperbolic relative to the collection consisting of parabolic subgroups in P1 and parabolic subgroups in P2. So this is the first thing. Second thing is, so I have G1 and P1, and I take a parabolic subgroup in this collection, so P. And suppose I have a group A such that P is a subgroup here. Then this guy, the amalgam over P, is hyperbolic relative to the collection P1, but now I remove P from P1, but I'm adding A, and P is contained in A, so we're not really changing a lot of things. So in the first case, I'm taking an amalgam over a quasi-convex subgroup, and I still end up with a relatively hyperbolic group. In the second case, I'm taking an amalgam with a parabolic subgroup. And the third one is similar. G1, P1, G2, P2. So again, relatively hyperbolic groups. And I take P in, so it's a maximal parabolic subgroup here. But in the second group, P sits inside as maybe a it could be non-maximal. Then again, taking the amalgam over P gives me a relatively hyperbolic group, and the parabolic collection is P1, but now I'm removing P from here in P2 because P is sitting inside a P prime here. So this was Dahmani's PhD thesis, and he showed that these groups are relatively hyperbolic by actually constructing a Bowditch boundary and showing that the actions are geometrically finite. Okay, but what is the point here? So, for example, for what I said about the above, we will use this statement because so in the mapping, so over here, if I take the mapping torus of a pseudoness of a map for the surface group. Okay, here it's surface with boundary, then it is hyperbolic relative to the mapping tori of the boundary components. So I'm taking an amalgam of that with a non-relatively hyperbolic group, say A. And because of the combination theorem, this guy will remain relatively hyperbolic, as given by this. Okay, so this is a sketch of the two theorems for the one-ended case. This was treated already by Gottero and Lustig, but in the combination theorem, it's easiest to say it. And now going to the general case. So the general case is proved by an induction on what is known as the Courot rank. So what is the Courot rank? So given any finitely generated group, so this is due to Grushko, there is a Grushko decomposition. So there is a maximal, okay, I'll change notation. So there is a maximal free splitting in this form. So why do I say maximal? Because these HIs here do not admit free splitting, so they are freely indecomposable. And the rank of, so given any other free Grushko decomposition of G, the free group we get will have the same rank. And the freely indecomposable pieces will also have only K of them, and up to conjugacy and permutation of the order, there will just be these HIs. So the Courot rank is this number K plus R. So the one-ended case corresponds to R being 0 and K equals 1. So for Courot rank 1 and one-ended, we have already seen it. The other case of Courot rank 1 is when K is 0 and R is 1. So the group is just a cyclic group Z. So there's nothing to show. So now let's assume the Courage rank is higher. So in this case, we need to talk about automorphisms, which preserve free factor systems. Okay, so here, so given a free decomposition of G in this form, these HI, so up to conjugacy class. So this is a free factor system. So a free factor system is a free decomposition of G, and the vertex groups up to conjugacy, when they're non-trivial, they're called free factors. And this is a free factor system. And given an automorphism, alpha preserves a free factor system if alpha permutes. So alpha, by abuse of notation, alpha restricted to H is a map. So it takes elements of H to elements of H. Okay, so because the Courage rank is higher, we do have a Grushko decomposition, which is not trivial, and we can talk about a maximal free factor system that is preserved by H. What does this mean? So, okay, I will maybe say the term. So alpha is fully irreducible with respect to H, a free factor system H. So there is a classical notion of irreducibility for free groups. Here it's for a free product. So it's slightly different, even though the idea is the same. So with respect to H, if given a free factor system Y, preserved by alpha, and each HI is contained in a conjugate of some Yj, then the free factor systems are equal. So yeah, by alpha, okay, that's for irreducible, and for fully irreducible, I want by any power of alpha. Okay, this is maybe slightly confusing, but I'm stating this just to say, okay, when we have this condition, then there is a theorem by Dahmani and Lee. It says if you have a free product, so yeah, so free product as above, and alpha is fully irreducible. Yeah, if alpha is fully irreducible with respect to a free factor system H, then first there exists a maximal collection of three polynomially growing subgroups. And two, the mapping torus is hyperbolic relative to the mapping tori of these guys. Okay, there is a slight I lied slightly here. So this is true up to saying there is some high complexity in the free factor system. What does it mean? So we have this free factor system. So we have a Passer tree. We need that there exists at least 2 orbits of edges in the Passer tree. So provided this, then they say with respect to the growth in the tree metric, we have this. But then in the word metric for the conjugacy length as I defined earlier, we use induction on the Kurosh rank because these subgroups, they will have lower Kurosh rank. This is also part of their statement. And they will be hyperbolic. So we get that these groups are hyperbolic relative to polynomially growing subgroups in the word conjugacy length. And so what we have is G is hyperbolic relative to some mapping tori, but each of these guys is hyperbolic relative to a further collection of subgroups. And it can be seen that this means that this guy is hyperbolic relative to this collection. This can be seen from either Osin's characterization of relatively hyperbolic groups or using Drutu and Sapir's characterization. I will not go into the details of those. Okay, so whenever we have a free factor system and alpha is fully reducible relative to that, and there is at least 2 orbits of edges in the Passer tree, then the theorem holds. So there are 2 remaining cases. So the remaining cases, first one is I have only 1 orbit of edges. So either it's a free product like this, or it's like this. So it's either an HNN or a free product. And alpha preserves this free factor system, so it sends H1. Okay, let me first talk about this. So alpha sends H1 to a conjugate of H1, but after post conjugating, I can assume alpha sends H1 to H1 and also H2 to H2. So I can assume this. Now, so here HI is again a hyperbolic group because it's quasi-convex in the splitting and it has lower Kurosh rank. So we use the induction hypothesis here. So we get polynomially growing subgroups. Of HI. So of H1 and polynomially growing subgroups of H2. But there may be more. And this can be seen by writing a word in its normal form and seeing when it will have polynomial growth. So first, there exists, say, these unique subgroups AI in HI, such that alpha of AI is not in a conjugate, but it is in AI, and it has polynomial growth not only in the conjugacy length, but actually in the word length. So then this A1 star A2 will also have polynomial growth in G. So this is the entire collection of polynomially growing subgroups of G. And we get this by using the induction hypothesis and the normal form. And the mapping torus, so this can be written as star T1, H2, semi-direct product T2, where we're identifying T1 with T2. So the first guy is hyperbolic relative to polynomially growing subgroups here, and the second guy is hyperbolic relative to polynomially growing subgroups here because of the induction hypothesis. And if this thing is non-empty, so it can happen that it is empty, then we will have to extend this collection. So what I can write, so I want to use the combination theorem. So I will write this as like this. So I'm using abuse of notation here. It should have been A1 semi-direct product T1 star A2 the semi-direct product T2, where we are identifying T1 to T2. T1. So then I can use the combination theorem. In fact, the second one for this, because and so this will be a group in a parabolic group in the entire thing. And this is the also of polynomial growth that we've seen here. So G will be hyperbolic related, sorry, the mapping torus of G will be hyperbolic related to the mapping tori of polynomially growing subgroups. So we get that when G is a free product. So this is done. And now the last case, which is also more tricky. So we have G's and HNN over a trivial group. So again, we use induction hypothesis. Okay, so before that, so I will assume that alpha sends H to H, and alpha of S is after some manipulations, there is some H, small h in capital H, such that alpha of S is H inverse. And I can again use induction hypothesis on H and say, okay, so I have a collection of maximal polynomially growing subgroups here. Is that all? Well, not quite, as we have more polynomially growing subgroups here, just one of them. We can have more here, in fact. So because of the way I have written the automorphism, so first I have polynomially growing subgroups of H. So this will be in my collection, but here I will remove one of them, and that is A, such that alpha of A is A, and A has word polynomial growth. Well, Why? Because I will put it in the next collection. So I may also have a subgroup like this, such that alpha preserves this guy. So B, so this, yeah, B is a subgroup of H, but SBS inverse is not a subgroup of H, but it may happen that this guy is preserved by alpha and has word polynomial length. So this may or may not be empty, but this can exist. And okay, so if I look at any element in the normal form, so I can write maybe H1. So this is a word written in the normal form for the decomposition, and where the powers are plus or minus 1. I can break any word like here into syllables of 4 types. So I have to analyze these things. So I may have S, H, H prime, S inverse. This is one type. I may have SH prime, H prime, S inverse, or just H prime. So I'm using H prime because H is already taken up here. So I don't want to mix notation. And when we analyze when these guys can have word polynomial growth, then we see, okay, there may be, in fact, especially this guy. So SH inverse, SH prime has polynomial growth, word polynomial growth. If and only if H prime belongs to this set, let me call it K. It satisfies an equation belongs to this polynomially growing collection subgroup. So once we have that, so this set K may or may not be empty. So then, depending on whether K is empty or not, I have to extend the polynomially growing collection by either this guy or this guy. For one of them. And why is this enough? Because when this is non-empty, this guy will be contained in the subgroup, and all the K's will be, so this K will be a coset of A. I'm not going into the details. So this is the collection. So polynomially growing subgroups of H, and this guy or this guy. Again, we use the combination theorem, and we can show that this, after writing it in some nice form, star a subgroup which corresponds to either this or this, and then we have an HNN extension over S. And we use the combination theorem to say, okay, this is relatively hyperbolic, and then we are going to a parabolic subgroup, so this whole collection is relatively hyperbolic. And this proves the theorem. Okay, so I'm done. I don't know if I ran out of time. I'm sorry if I did.
You're just finished on time, pretty much.
Great.
I mean, if you have some quick remarks you would like to conclude, you still have a couple minutes, that's fine.
Well, okay. A corollary of this result is if alpha is an automorphism of G, then any element for every G, this growth, there is a dichotomy. Either this grows exponentially or it grows at most polynomial. So there is no intermediate growth happening here. This was already seen for surfaces by Thurston, and this result has also been proved by Orbes, Orbes, Coulomb, Helion, and Girardel. I think I might be wrong with the names, but yeah. So we get this as a corollary of the relative hyperbolicity, and given an automorphism. So another corollary is this guy is hyperbolic if and only if. So it's not really an interesting case. G is a free product of, so G is a free product of some surface groups and a free group. This is the only case. And alpha acts as a pseudo-Nosov map on each of these surface pieces and a toroidal map on FR. There won't be any new hyperbolic group. Yes, that's, yeah, I'll stop here.
Okay, thank you, Suraj. Do we have any questions? Well, if nobody doesn't, nobody else has, I have a short question. So, like hyperbolic groups and relatively hyperbolic groups, they also can have quite interesting algorithmic properties that certain things are decidable in them. So I'm curious, like using your results, does one get like new decidability results for groups that were not known or were like open?
Well, I'm not really sure. For hyperbolic groups, just for hyperbolic groups, so for G, any algorithm that you want it already exists, I think. And when you take a mapping torus, well, it's okay. This result is saying it is relatively hyperbolic, but maybe there can be an algorithm to find out whether it is what its parabolics are. I'm not sure if that does not already exist.
Yeah, I don't know much about the problematics of mapping or a relatively hyperbolic group, so I was just curious.
Okay.
All right. Any other questions from anybody else? Seems like not really. So in that case, let's thank Suraj one more time. And yeah, Suraj, thank you for the talk.
Thank you.